So this is 4.4, the fundamental theorem of calculus. Fundamental theorem of calculus. Sounds important. Calculus. Oh, goodness. And the fundamental theorem of calculus has to do with integration. Theorem of calculus. Theorem of calculus. Has to do with integration. We have two integrals that we have done so far, right? The first integral, called an indefinite integral. Indefinite integral is aka an antiderivative. An antiderivative where you are finding, right, if this is f prime dx, if you have a derivative in there, you get back the original equation plus c. Right, we have our indefinite integral, which is aka an antiderivative. Basically, right, the rules we saw, like the power rule, taking the integral of sine gets you a negative cosine, right? All those integrals and derivatives, that sort of connection, that the integral of secant squared is tangent. All those rules of integration we do with an antiderivative. We do the indefinite integral. We also have a definite integral from a to b equals the area under the curve, called the definite integral. Definite integral. And we can find these areas with graphs. If you're given like a graph of information, you can find the area. We estimated the areas with things like Riemann sums. But we did not have a way to exactly calculate any function in here. We do not have yet a way to calculate the area, the actual exact area under a curve with a definite integral, if it's not like using geometry. Right? We have the geometrical ways we've done it. We have the Riemann sum ways we've done it. But we don't have a way yet to do it for any equation. So the fundamental theorem of calculus, what it does is it ties these two together. It ties these two together and allows us to have a way to find any area of a definite integral using what we know about indefinite integrals, using an antiderivative. Fundamental theorem of calculus bridges these two together, and we have the following rule. If you do the integral from a to b of f of x dx, so we're doing a definite integral of some function, that is exactly going to be equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. And this is the fundamental theorem of calculus. Capital F is the antiderivative. Capital F is the antiderivative. Antiderivative. And so you use the antiderivative. You say, well, however much I gained from going, or from wherever I started at b, minus wherever I started from a, wherever I'm ending up at b, whatever my antiderivative ends up at with b, minus where I started with was from a, is equal to the area. It will exactly equal the area under this curve, right? So it's my ending sort of like amount, ending amount, minus the starting amount equals the amount changed, or added or grown or added And this is the fundamental theorem of calculus. We have this ability to find antiderivatives, and when we find an antiderivative at a particular value, what you are finding is the amount of growth, the amount of like accumulated stuff, right? The area at the ending minus the area from the beginning. You subtract those two, you get the change in area. You get the change in amount. And that change in amount is equal to the total, exactly equal to the total amount of the curve under the integral. And so this is the fundamental theorem of calculus. Fundamental theorem of calculus. Maybe I should do that below. Hold on. Let's go like this. Fundamental theorem of calculus. Let's put it down here. Fundamental theorem of calculus. Remember, an integral is an area. And so when you find an antiderivative, you find the antiderivative, and you plug in the ending amount, that'll give you how much you have, how much your equation grew at the end, how much you have at the end. And you subtract how much you have at the beginning, wherever you started from, right? You have A here, wherever you started from. Those two amounts subtracting each other gives you the amount that you grew, the amount that you changed, the amount that you added to the function. And that's what we're looking for. The amount is the area under the curve. So let me give you an example of how we do this. Find the area under the following curve. So let's say I have an equation that looks like this. 1, 2, 3, 4, up to 2, from 0 to 4. This is f of x equals negative, I think it's 1/2 x squared minus plus 2. Oh, goodness, hold on. Plus, no, minus 2x. Things like that. Hold on, let me just verify this. I'm making up this equation, no one. Hold on. Sometimes I need to check what I'm doing. One half x squared, not 1/2 x squared plus 2x minus negative 1/2 x squared. Yes, negative 1/2 x squared plus 2x. Perfect. Plus 2x, plus 2x, plus 2x, plus 2x. So I want to know the area right here. I want to know this area from 0 to 4. I want to find that area under the curve. Negative 1/2 x squared plus 2x is the curve here. This is our equation. Tell me the exact area. Before, all we could do was use the Riemann sums and split it up, maybe get an estimate. Over, under is kind of like averaged, right? But we want to get the exact area. And we have this fundamental theorem of calculus now that lets us do this equation. So if I take the integral from starting here, I'm starting at 0, over to 4, that's how much I'm changing, of my equation, negative 1/2 x squared plus 2x dx, and I do that integral, I'm going to get the antiderivative of this equation. I'm going to do the integral the same way we did before, just like last time, where we are doing the antiderivative, right? We're doing each part, and then we're going to plug in our values of 0 and 4, subtract them, and get the amount of area under the curve. So this is the exact area. So let's find our antiderivatives. What is the antiderivative of negative 1/2 x squared? What does this become? Antiderivative, right? Remember our rules here? Going backwards up the chain. So it's going to be negative half is still there. The negative 1/2 stays in front. And the x squared becomes x to the 3rd power over 3. Right? Plus, so that's that part. This part antiderivative, the 2x, what does that become? Well, again, the 2 stays in front. X becomes x squared over 2, which I can simplify this. This is going to be negative x cubed over 6 plus x squared. That's a squared. All right, my antiderivatives. Notice that I am not using a c anywhere in this equation. I'm not finding a formula. I'm finding a value. I'm finding an a numerical answer. This is going to give me a number. This is going to give me an area. This area, this integral here, gives me the area, exact area under the curve. So what we're going to do is we're going to say, okay, well, this integral, I found the equation here. This is my f of x. Right? This big equation here, this is capital F of x, right? My antiderivative, my capital F of x. This equation is the antiderivative of what's inside here. So to find my area, I'm going to take capital F, I'm going to plug in the b, which is my 4, minus the antiderivative, plugging in the 0. I'm going to plug in those numbers into my antiderivative equation, into my f equation, and that's going to give me the area. So let's find out, let's see what we do here. Let's see. First one, I'm going to put in brackets here. Negative 4 cubed over 6 plus 4 squared. That's my first one. Minus negative 0 cubed over 6 plus 0 squared. Okay? Let's see what I got there. I took my equation, my antiderivative equation. I plugged in my 4, f of b, minus f of a, b minus a. Plug in the 4, get my numbers. Plug in the 0, get my numbers. What's this going to be? 4 cubed is, let's see, 64, is that right? 64? 4 times 4 is 16 times 4 is 64. Yeah, so 64 over 6, negative 64 over 6, plus, that's going to be 16, right? Minus, well, that's clearly a 0. Start with 0, that's going to be a 0. 64 over 6. 64 divided by 6 is 10.6, repeating. So it's negative 10.6, repeating, plus 16, which is going to be, what is that going to be, 6.6, repeating? Probably, hold on. 64 over 6 plus 16. 5.3, repeating. 5 1/3. 5.33, repeating. So that is the exact area under that curve of that equation. F of b minus f of a. So this gives us an exact way to find it, exact way to find these answers. And this is why it is the fundamental theorem of calculus, because finding this area, finding the accumulation of the amount the graph has changed over time. Let's say this was this graph represented like a speed. Let's say this was a velocity graph. If this graph of f was velocity, the integral of velocity equals distance. So in, I don't know, 4 hours, you traveled 5.33 miles, is what this would say. So if our velocity, we start at a stop, we gain speed, we reach some maximum speed, we slow back down, and then we stop again. This is our velocity graph. Right, if you're imagining this is like speeds, right? This is like speeds. We gain speed, we reach a maximum speed, then we slow down, and we stop. That distance we have gone, the distance we've traveled there, we can find that using the integral, using this integration. So if this was velocity, the integral of velocity gives me distance. So in those 4 hours, I've traveled 5.33 miles, or whatever your units are. This is meters per second, then we've gone that many meters and that many seconds, whatever your units are. And so this is a very powerful tool in our repertoire. And we can do this with any kind of equation. Right? We can do the fundamental theorem of calculus with anything that we can integrate. So let's try another equation. I'll give you this one here. Find the area. Or let me say, instead of find the area, I should say find the amount of change in f from, let's say, I'll go from 1 to 2. Find the amount of change. Same kind of thing. Amount of change is the same thing as meaning area under curve. Area under curve. Area under curve. When I say the amount of change or the growth that happened, right? How much change occurred, the amount of change, to find out how much changed, we do an integral. So if my f of x, let's say, is equal to 1 over x squared. 1 over x squared. What does that graph look like? The graph looks like this, and then like this. From 1 to 2, we are looking for the area under here. My equation is 1 over x squared. We're looking for the area under that. So to find this area, we do the integral. At the integral from 1 to 2 of 1 over x squared dx. So what's the integral of 1 over x squared, everybody? Integral of 1 over x squared. Well, we don't like it when variables are on the bottom, right? So we can change this to be the integral from 1 to 2 of x to the negative second power, right? Remember that? And then if we do the integral, we know how to do the integral, right? We just add 1 to the top. Negative 2 plus 1 is negative 1 over negative 1. And there's your f of x. Okay? So there's your f of x. So now I'm going to say this is f of 2 minus f of 1, right? F of b minus f of a. You always start from the end, go backwards. When you're finding amount of change, you're always, just like your distance on a ruler. You want the end minus the beginning. That tells you how much change happened. So I'm going to plug in my f equation. Let's see, I'm going to have, well, it's really 1 over x, negative 1 over x. So it's really negative 1 over x. So let me just use that. Negative 1/2 is my first part, minus negative 1 over 1. So let's see, negative 1/2, that's negative half. Minus negative 1, that's going to be plus 1. Oh, well, negative 1/2 plus 1. That's a half. Easy. Okay? Question about this? Concerns, worries? Now that we know how to do an integral, we can... There's a fly, everyone. Making me crazy. I think it's gone. Alright, now that we know how to do an integral, we can use that with this fundamental theorem of calculus, to find the exact areas under, again, anything we can integrate. Let me do one more example. We have 10 minutes left. Let me do one more example. Your homework is going to be trying some of these questions and making sure that you know how to work them. So let's do something a little more complicated. What's a good one? What's a good one? Ooh, that's a little too complicated. Here's a good one. 0. Okay. What if I do find the area of the integral from 0 to 2 pi of the sine of x dx? Find the area of the integral of sine of x from 0 to 2 pi. So one full cycle of sine, how much area is under the curve of that equation there? Again, from the sine, you do the antiderivative. So what's the antiderivative of sine, everyone? In the chat, someone tell me. I'm not going to do this one for you. You've got to figure this one out. What is the antiderivative of sine? What is the integral of sine? What equation if I do the derivative? You're close, you're close, you're close, you're close, you're close. Something is missing. Thank you, Stephanie. Thank you, Percy. Yes, negative cosine, because when you do the derivative of cosine, it's negative sine, but this is not a negative. So this is negative cosine of x. Yes, very good. And there's our f of x. So we're going to plug in f of 2 pi minus f of 0. So negative cosine, and put this in brackets, negative cosine of 2 pi minus negative cosine of 0. What is that? Oh, I got to remember what the cosine of pi is, how pi works. Yes, I do. You will need to know how to find the value of these various trigonometric equations. You can do this with the cosine. You can do this either with the unit circle. either with the unit circle, right? 2 pi, cosine of 2 pi is here. Cosine is the x direction, that's a 1. Since it's negative, it's negative 1. Or you can do it with the graph of cosine. Graph of cosine. Graph of cosine. You can also think of the graph of cosine. Cosine graph looks like this, right? At 0, it's up at 1. And then at pi over 2. At pi. At 3 pi over 2. And then at 2 pi, right? 2 pi back up to 1. So you can do it with the graph of cosine or the unit circle. These are both, right? These are equivalent systems. However your brain works better. 0 and 2 pi, right? So yeah, negative 1 for the first one, because it's a 1, and then we'd make it negative. Minus negative 1. Oh, interesting. Negative 1 plus 1. That's a 0, everybody. What? What? How is the area under the sine graph from 0 to 2 pi as 0? How is it nothing? Why do we get an answer of 0 here? Well, let's look at the sine graph and try to remember how it works. Here's 2 pi. Here's pi. Here's pi over 2. Pi over 2. And here's 3 pi over 2. Do we remember what the sine graph looks like? Where does sine start? Cosine starts at 1. Sine starts at 0. Goes up to 1. Goes back down to 0. Back down to negative 1. And then back up to 0. So if we draw the sine graph, right, it's going to look like this. It's going to go up. And then it's going to go back down. Come back up. And so from 0 to 2 pi, we found the area, I should say up here, and the area down here. Oh, anybody see it? Anybody see what's happening? Why is it 0, everybody? Someone explain in the chat. Why does our area turn out to be 0? This area here and this area down here. Why does the area turn out to be 0? Anybody have an explanation? What do we remember about areas? Yes, thank you, Perry. So exactly, the areas are positive or negative, canceling each other out. That is perfect, exactly. So this area here is above the axis, this is positive area. This down here, remember when you're below the x-axis, this is negative area. And the areas are equal, exactly equal. Sine is a symmetric function. The areas above and below are exactly equal. So they cancel. So they cancel. Yes, very good, very good. Now, bonus question. Bonus question. Find the integral of 0 to 2 pi of the absolute value of sine. Ooh. What does that do? Bonus question, what's the absolute value of sine? Two. Why is that, Perry, so? Did you plug it in a calculator, you got the answer? Is that why? Well, the trick here, and let me just show you this trick, is when you have the absolute value of sine, the graph of the absolute value of sine, 2 pi, pi. Yes, the absolute value sign makes the negative value positive. Exactly. The absolute value sign, what it does, pi over 2, this is 3 pi over 2, is it takes the graph of sine, right, which normally looks like this and then goes down below. Instead, it bounces it back up. Bounces it back up, right? So our sine graph goes above the axis, and then instead of going below, right, it flips it and puts it back into positive. So basically, it's equal to 2 times the area from 0 to pi of the sine of x. Basically, if you find the area of one of these little sections of the graph, it's going to equal 2 times that because it's the same thing twice. So if you found the area from 0 to pi of sine, which is going to be equal to 1, multiply that by 2, you get the area of 2 here. 2 times the area from 0 to pi, right? It's twice the area, makes it doubled. If you find one of the areas from 0 to pi, find this area here, multiply it by 2, you get the whole thing. And yes, absolute value, what the absolute value does is it makes the area below, instead of bounces it back up to being above the x-axis. And so all the area is positive, and you got to kind of have to deal with that by seeing where that change happens and integrate the section that you need one piece at a time, basically. So that's going to be a whole other thing. But very good, little bonus question. All right, your homework. We're out of time. Your homework tonight is going to be doing some of these integrals. 4.4, page 292. I want you to do numbers 9 through, I think it's 33, every other odd. So like 9, skip 11, do 13, da-da-da-da-da, every other odd. And then I want you to do 37 to 40 all. So that's your assignment. Find the areas under those curves. Use the integral stuff. Due next week on Monday. Tomorrow we will have another meeting during the office hour time from 1:30 to 2:30. What do you think this is? It's not regular calculus, Jessica. It's AP calculus. Hello. We will have another study session tomorrow in the afternoon. I hope to see you all there. We can go over this assignment then, if you would prefer. Maybe I'll just post the review. Either way, I will see you then. In the chat, type goodbye. Once you type goodbye, you're free to go. Thank you very much, everyone. I'll see you next time.